Hello and welcome to Data Science in Industry vlog. This is the third video about the topic of integration of AI methods with a control system. In the first video, I was discussing the distributed control systems. In the second video, I was discussing typical algorithms that are used in the control layer. So I was discussing the PID controller, feed-forward control, and cascade control. Now I would like to use this knowledge about DCSs, about typical control structures, to show you how we can read the data from the control system, but also how we can send the data to the control system, and how the control system can transfer this data, let's say optimal decisions, for instance, to devices. In a safe way, of course, safety first. So there are many ways how we can exchange information between the control layer of a factory or a plant and the AI method. We can use one of the many industrial protocols to exchange the data. We can use dedicated drivers provided by the DCS system or the SCADA system, if the SCADA system is in the factory, or the BMS system, so the building management system, if we are doing the project in the field of intelligent buildings. Nearly all of those systems, I mean DCS, SCADA systems, right, PLCs, BMS systems, nearly all of them supports OPC standard. What is the OPC? This is the OLE for process control. So if we don't know how to read the data from the control layer and how to send the data back to the control system, probably the OPC server would be a solution. It's not the only possible solution. Like I tell you, you can use dedicated drivers or other protocols. For instance, if you would like to connect to the building management system, probably the BACnet protocol would be the one you will choose, because this is the most popular protocol in BMS systems. But by default, the OPC server could be a solution. So we can treat this OPC server as the solution that helps us translate different industrial protocols into one unified, well-known protocol. And of course, we have to connect to the control system somehow, because we have to read the data in order to analyze them using, I don't know, some optimization algorithm or the deep neural network, because we need to check or evaluate the risk of device failures, or we have to calculate optimal decisions on how to use a set of devices that are part of the industrial process. And of course, later on, we have to at least inform the operator, the dispatcher, about threats, about recommendations, how to use those devices. But also maybe we can send those the decisions directly to devices using the control system of a plant or the factory. So right now I will tell you how to modify control algorithms so they are able to get our decision, our AI method decision, and send it further to devices, and how to do it safely. I will also discuss how to modify operator graphics so the operator is aware of results of the AI algorithm. Okay, so let's jump into the first part, the modification of the control system. So first of all, where is our AI method? Suppose we have a distributed control system. It consists of the controllers, right? Input-output modules. It consists of sensors that measures current, flow, temperature, device load, valve opening level, etc., etc. And actuators, pumps, valves, feeders, and those are the actuators. Moreover, we have some computers connected to the plant network, to the network, like operator stations where the operator can observe the process, and also it can decide about what should be the valve opening level, which pump should be used, etc., etc. And engineering stations where we can create new variables, new process tags or process points that, for instance, represents outputs of an AI method. So it can represent decisions calculated by the AI algorithm. So first, if we know that our AI algorithm will decide about which pump should be running and what should be the load of each pump, we have to create such process points like pump 1 load by AI method, pump 2 load by AI method, right? Because the AI algorithm will write into those points. And one of the PCs that are connected to the network can be utilized for the AI method. So AI algorithm will be executed on this computer. So the AI algorithm will be able to read the data from sensors via controllers, so in fact from controllers, right? Calculate optimal decisions and send it back to controllers, and then through the I/O input output modules to actuators. And of course, those decisions should be presented to the operator, all right? So the operator is aware of what the AI method is doing. Right? He can control which devices can be supervised by the AI method, or he can just turn the algorithm off if he don't like the results of the AI algorithm. Of course, if we are only reading data and then calculating some, for instance, the risk of the device failures, we can put our AI algorithm in the cloud, right? If the cybersecurity of the plant or the factory allows for it, and we can do our computation in the cloud and then present it to the factory or the plant staff in the form of some BI reports or interactive dashboards. But if we would like to present it to the operator in the operator station, and if you would like to send those decisions back to devices, this PC should stand with other PCs connected to this highway in a plant or the factory. Now suppose you would like to send the optimal decision calculated by the AI method to the control system. For instance, you would like to send the optimal value of the set point for a temperature or for the oxygen level or for the flow or for the pressure, because you know that with this set point, the costs are the lowest, the incomes are the highest, there is the lowest emission of harmful gases, the lowest risk of a failure, etc., etc. Right? Some measure of efficiency, some optimization goal is satisfied if the process will utilize this particular set point from the AI method. So As you remember, the PID controllers are the most popular algorithms that tries to get the output of the process, the measured value, to the set point value. So if we have some set point of temperature here, the PID controller will calculate such a control signal and it will send it to the device. Maybe it will, I don't know, open the cooling water valve so that the measured temperature is as close as possible to the set point. It tries to minimize the difference between the set point and the measured value. Please take a look on video number 2 in order to understand this closed loop. Alright, so usually the set point is calculated by the, or is, let's say, the operator decides about the set point, or in more complex system, the set point is calculated based on other factors, other signals. I don't know, if we have a high load of our industrial process, maybe we would like to have a higher temperature, so the set point is calculated based on some function, based on some characteristics that is based on other process parameters. And of course, the operator has an option to add some bias, add few percent more or few percent less to the set point that is automatically calculated based on other process parameters. Of course, if we are running in the auto mode, right? Because operator can always change to manual mode and he will decide directly about the value of the control signal that is sent to the device. For instance, about the opening level of the cooling water valve. But of course, if we would like to send the decision from the AI method, the control loop here should operate in automatic mode, right? So we need to do some modifications to allow the control system to read our information. We have to add a hook here. So what we should do, we should register a new variable, new process point that is called, I don't know, the set point from the AI method, right? And the AI method will write to this point through the dedicated driver or via the OPC server, right? But it will write the value of this point. It is good to add some rate and value limit. So even if the AI method will calculate something really stupid, it will be limited to reasonable values here. And moreover, if the AI method will calculate some stupid things, the transition from the previous value to the new value will not be instant. There should be some rate limit, so the operator can see that this set point goes to some strange location, some strange value, and he has a time to react. Safety first, right? Then we have this if-else statement. This is the algorithm that pass this information if the flag connected to this algorithm has a high value, or it pass this information if the flag connected to this algorithm has a low value. So if this flag is equal true, the decision made by the AI method will be sent to the PID controller as a set point. If this flag has a false value, the original set point will be set to the PID controller. Later on, I will explain you how to calculate the value of this flag. Now we have to remember just that there is such a if-else statement. Moreover, you remember tracking, right? I think I was discussing this in video number 2. If the flag has a true value, so the AI method calculates the set point, the tracking should be we should enable tracking here up to the operator bias. So the operator bias is automatically recalculated in such way that on the end, here we have the same value of the set point as the AI method. And the same thing should be, the same tracking should be enabled if the flag has a false value. So if the AI method is disabled, or maybe it's disabled, it's not sending the values to the control system, the tracking should be passed here. So this process point that represents the decision of the AI method will be automatically recalculated in such way that the value of the set point calculated by the AI method would be the same as the original set point. So we need to do this because if the AI method will be turned on, it should start from exactly the same point as from the current point, right? From the current value of the set point. This transition should be bumpless, right? For the safety reasons. And that is why the AI method should track the value of this point, should be aware where was the process just before my calculations, the AI method calculations. All right, and this is, okay, I should also mention about this. If we have this manual auto station here, and usually we have it below the PID controller, we should also add one more state to this manual auto station, the AI supervision. Right? Of course, we will not do this in the control system because this algorithm handles only two states, manual and auto. But we can show the operator on the operator graphics that right now the AI method supervises this control loop. And auto mode would be the mode where the control loop runs in automatic mode, but the AI method is disabled. All right, this is one way how we can send our decision, how we can modify the control algorithm in order to send a decision to the control system. Here is another way. In such architecture, the AI method calculates the optimal value of the operator bias, right? So the hook is here. If the flag has a false value, the operator bias is sent to this algorithm that adds this bias to the original value of the set point. If the flag has a true value, then the operator bias tracks the AI method decisions, and the AI method calculates the optimal value of this bias that is added to the original value of the set point. And to be honest, I prefer such a architecture because if there is some logic here, right? For instance, if we are calculating what should be the optimal value of the valve or the air damper opening level, it usually depends on some external sources, right? If we are increasing the load of our industrial process and for instance we need more air, there is a characteristic that says if you increase the load, please increase the set point for the airflow, right? And usually it is done because some smart guys, some engineers calculates where are the safety values of the airflow for different operating points. And we should not change this. But what we can do, we can slightly modify it by calculating the optimal bias. Maybe by reducing this airflow, this set point for the airflow by a few percent, we can still operate in a safety region, but we can generate an essential cost reduction. And like in the previous example, there should be a rate and a value limitation. Just in case the AI method calculates some stupid things, we will make an error or whatever, there will be some connection error. And the rest is unchanged. If you would like to implement the AI method that controls devices, we should also implement the logic within the control system that decides about the value of this particular flag, right? So, we also have to change the operator graphic and, let's say, add the button that represents the state of the AI algorithm. So the operator can turn the AI algorithm on or turn it off. There are some one or two buttons, right? And here is the algorithm that is connected with this button, right? It passes the information about the decision of the operator to this flip-flop. So if the operator decides that the AI method should be started, on the end of this flip-flop, we have a new state which is equal to true, which means that operator decides that AI method should be started. But of course, we should also check if the AI method is present, right? So if there is a heartbeat signal or other signal sent from the AI method to the control system that presents that the AI method is alive. If we will not detect such a signal, then we can reset the flip-flop and this decision is changed to AI method is turned off. So the operator wants, he might want to turn it on, but because there is no connection, maybe there's no connection, or there is some failure of the AI method, it cannot be enabled. Because this is for safety reason, of course. Moreover, we can check the plant or the factory conditions if the plant or the factory is ready to cooperate with the AI method. Maybe our AI algorithm was trained on the data from particular process operating point, and we have to check if we have such a process operating point. Maybe this algorithm was trained and developed for the normal process operation, not for startups. And if we check that there is a startup, let's say the load of the industrial process is rapidly increasing, then we can say, oh no, those are not conditions for the AI method. The AI method was not tested and not trained on those conditions, so we should turn the AI method off. Right? Moreover, the AI method decides about particular devices. In this particular example, it decides about the left air damper, right air damper, and the set point for oxygen. Right? So we have to check if those control loops are related with those devices are operating in the automatic mode. Because if they are operating in the manual mode, what can we do? Nothing, right? The operator has the full control over devices. So we have to check if all of those devices, or let's say 80% of those devices, are operating in auto mode. If not, then sorry, the AI method has to be turned off. But if yes, if the operator says, yeah, let's go with this AI algorithm, the communication is working properly, the process state is okay, this is a typical process state that we know that the AI algorithm will operate correctly for these conditions. And there are no problem with control loops related with those devices. There are no problem with those devices, so they operate in automatic mode. Then we can change those flags here to true. Then and only then AI method can pass the information to the control system and further to devices. Yeah, so let's take a look on one particular device. Let's say this one. If it operates in automatic mode, if the control manual auto station of this device is in the automatic mode, and this main signal says that, yeah, let's turn the AI method on, it should be turned on, then this flag associated with this particular device is set to true. And the AI method passes the information to the PID controller, and the operator bias here is tracking the decision of the AI method. I also like to extend this architecture a bit. So I would like to, and I recommend you to do it, to give the operator the possibility to decide which devices should be operated by the AI method. For instance, if we are controlling forced draft fans in the power plant, first of all, we have to check if those two devices are the manual auto stations associated with those devices are in automatic mode. And if so, we should check if the operator allows the AI method to control those fans. So there is an additional button on the operator graphic. For each device or for each classes of devices, there is a separate button, and the operator can decide that, okay, AI method, you can play with air dampers, you can play with the oxygen level, but there are some problems with those fans today. They operate, they generate strange noises. So today I would like you to skip those forced draft fans. You can play with other devices, but I will not let you play with those forced draft funds. You should look for savings with the utilization of other devices, right? But if there is, if the operator will say, okay, go ahead with those funds, and those funds will operate in auto mode, and all other conditions are satisfied, so the operator allows for AI method, there is communication, and the factory or the plant industrial process conditions are okay, then a particular flag, this particular flag associated with forced draft fan would be set to true. And here is the algorithm that presents how you can check the heartbeat signal. If there is a heartbeat signal, I will not go into details because you can choose other signals like let's say a SAW signal that is rising, or other communication protocols. Well, maybe not communication protocols. Our ideas how to exchange the information about the alive status of the AI method. This is just an example. On the end, we have information that the heartbeat is present, so the communication is there, or no, or the information that the AI method is dead, and or there is no communication. Right, here you can see an example of the operator graphic. So like I told you, we have some panel where we can start and stop the AI algorithm. In this particular case, this is the optimizer that is based on the analogy to the immune system operation. So this is the artificial immune system that optimizes the plant operation. It minimizes the CO and NOx emissions, and it tries to increase the efficiency. So first of all, this panel, start and stop, right? And this panel can be associated with this algorithm, right? That sets and resets this flip-flop. Then you have a panel where the operator can say that, dear AI method, you can use the oxygen set point to minimize CO and NOx emissions. You can, I don't know, use the OFA dampers, SOFA dampers, feeder speeds, forced draft fans, but you cannot use induced draft fans, right? The operator can click no. This is something that you cannot use right now. Right, so this is those buttons will set the value of this particular signal. It can be true or false. Moreover, it is good to show the states of all the operator stations. I call it operator stations of all the devices that are controlled by the AI method. So the operators see what is the set point for air damper, what is the set point for oxygen, right? What is the state, if it's of this operator station? Is it automatic mode or is there a manual mode? So he can have a full control over the operation of the AI method. We can give him the possibility to show the trends, time trends of the parameters that are controlled by the AI method and the decisions made by the AI method. All right? Okay, so this is something that we have to develop during the implementation, or we can ask plant or factory engineers to help us or to do it, right? So we will just draw a picture on the piece of paper, in Paint or PowerPoint, right, or other IT tools, and we will explain them. What are the functions of those buttons? Why we would like to show the operator stations here, right? And they will do the job with us. The same here. We are experts in AI methods, right? So this is something that if we need a support in creation of those logics, we can always ask the plant staff to help us. It's not very complicated, but if we are not sure how to do it, it's better to ask for help, because this is a crucial thing from the safety point of view. Yeah, and one more remark related with the operator stations. Like I told you, if we are adding the AI method to this decision path, we should inform the operator what is the state of the particular control loop. If it's in manual mode and the operator has a full control, full responsibility for this particular device, left air damper. If it's in auto mode, so normal operation, the PID controller decides about the damper opening, or based on, let's say, typical control strategy, or we have a AI supervision mode, where this particular device is controlled, or maybe device, the set point for this device is controlled by the, is calculated by the AI method. We can also add some information about the state of the AI method. Here you can see that there is additional information about the state of the learning process, right? Because you can also add here a button, a panel with buttons that allows the AI method to learn from the most recent data, or to stop learning from the most recent data, because we do not trust the most recent data. So this particular algorithm learns, increase the knowledge about the process by observing process reactions to control changes. So it stores those reactions to control changes in a database, and later on it uses most recent reactions for the gathered in the close neighborhood of the current process operating point. It uses those data, breaks those information to create a model on the fly, the predictive model of the process, and do optimization based on this model. So, but if we do not trust the data right now, because there is some sensor calibration or there is a failure of a device, we can add additional panel with buttons, and the operator can say, okay, dear AI method, stop learning right now, because you trash in, trash out, right? You will learn from the data that are corrupted, that had a bad quality. And of course, he can turn the learning on when the quality of the data is okay, is acceptable. I will make an additional video about the automatic updates of the model, about the model adaptation to current conditions based on most recent data. Okay, I think I covered the most important things related with the integration of the AI method with the control system. If you have questions, if something is unclear, please write in comments or write me an email, and I will try to explain it better. On the end, I would like to wish you a happy new year and lots of interesting projects in upcoming year. Let the force be with you.